Welcome to this explainer. Today, we're taking a hard look at the AI hype cycle. We're going to logically dismantle this idea that bigger is always better when it comes to AI models and systematically prove out a highly efficient, mathematically sound alternative to all that massive parameter bloat we see in frontier models. Just to set the stage here, let's contrast the sheer massive compute of standard autoregressive LLMs, the ones packed with billions of parameters, against what we call tiny recursive models, or TRMs. We're talking about a completely different beast here. TRMs operate on a tiny 7 million parameter footprint. That is literally a fraction of a percent of a standard model. It really demands that we ask a tough question. Is there a smarter way to scale reasoning without just endlessly buying more GPUs? So, we aren't going to hit you with fluff. Here's exactly what we'll cover. 1. The problem with massive LLMs. 2. The recursive reasoning alternative. 3. Escaping deterministic bad basins. 4. Inside the Graham architecture. 5. Real-world execution and proof. And finally, 6. Production-ready training infrastructure. Section 1. The problem with massive LLMs. Why bigger isn't always better. Let's start by steel-manning the status quo, so we understand exactly where these massive models hit a mathematical brick wall. When you break down neural reasoning right now, you quickly realize autoregressive LLMs are essentially locked into sequential, single-path trajectories. Because they generate reasoning token by token, taking a wrong turn early on means the model is, pretty much doomed. It rarely recovers. This strict single-path constraint is exactly what forces developers to just throw billions of parameters at the problem. They're basically hoping the model memorizes enough data to simply never make a mistake in the first place. Section 2. The recursive reasoning alternative. Rethinking the architecture. What if we completely decouple reasoning depth from parameter scale? What if we don't actually need billions of weights to think deeply? Enter the tiny recursive model. A TRM utilizes a single, small network to iteratively refine an idea, or a latent, through nested loops. Instead of passing data linearly through hundreds of distinct heavy layers, it cycles that data back through the exact same tiny network. It's a really elegant solution. It achieves profound reasoning depth by essentially rethinking, completely avoiding that massive parameter bloat. Now, I know the skeptics listening will spot the vulnerability immediately. It relies on a single deterministic path, right? If k equals 1 and your tiny model makes one wrong assumption during that loop, it gets stuck. It completely traps the entire process in a failed state, just endlessly refining a totally wrong answer. And that's a very fair critique. Section 3, Escaping Deterministic Bad Basins, the mathematics of noise. So you might be wondering, how on earth do we fix that trap? How does injecting random noise actually solve a problem instead of just destroying the data? Think of a deterministic bad basin, like being stuck at the bottom of a steep valley. If a single, rigid process gets stuck down there, it has a 0% escape rate, no way out. But by running 100 probabilistic rollouts, we intentionally inject standard deviation noise into the process. The data proves this noise actually acts as a sort of kick. It bounces the trajectory out of that bad basin 8% of the time, allowing it to hop the ridge and actually find the correct solution. It's brilliant. Section 4. Inside the Graham architecture. How it actually works. Okay, so the theory is mathematically sound, but how is this structural framework actually built under the hood to execute these rollouts? The core inference algorithm relies on two simple dimensions. We run k parallel rollouts, which represents our width, while executing d deep recursion steps. By injecting Gaussian noise at each step, we purposefully create multiple parallel realities for the model to explore simultaneously. But of course, noise alone is just chaos. The absolutely crucial step here is that all these noisy parallel trajectories are filtered through a pre-trained Q-head. Think of the Q-head as the ultimate judge. It evaluates all these messy parallel paths and optimally selects the single best, most logical trajectory to push forward. It brings order to the chaos. By combining these elements, the Graham architecture generates what we call a probabilistic trajectory tree. The model gets to explore multiple valid hypotheses all at once. It's exactly like a chess grandmaster playing out different moves in their head simultaneously. And the best part? It does this efficiently without needing a massive billion-parameter network just to hold the context of every single branch. Section 5, Real-World Execution and Proof, From Theory to Empirics. Theories and diagrams are nice, but any true critic demands empirical data. So let's look at what actually happened in the local runtime logs. During a Sudoku Extreme simulation, the system was configured to run 20 parallel stochastic trajectories, and the local execution logs explicitly show escape events successfully firing. This proves the system possesses the real-world skill to self-correct. The stochastic noise literally bounces the trajectories out of dead ends, and it does it without requiring human intervention or massive server farms.
Furthermore, we have the hard metrics to back it up. The empirical logs show that the validation loss successfully decreasing, eventually stabilizing right around 2.73 over 100 training epochs. Why does this matter? Well, it proves that despite injecting all that noise, the deep supervision signals are driving the model accurately. It is learning, and crucially, it's remarkably stable. Section 6, Production-Ready Training Infrastructure, Engineering Reality. Finally, any serious software critic is going to want to know, is this just some isolated script for an academic paper, or is it a deployable engineering reality?
The backend mapping confirms a highly robust production-grade REST API with precise post and get methods. The system is explicitly designed to asynchronously manage, track, and cancel multiple parallel training jobs, all entirely in memory. This is built for the real world. The tech stack itself is brilliantly optimized. We're talking about a lightweight Python backend featuring fast API, tracked by a React frontend, and utilizing local SQLite state management. But you know what the most staggering metric is? The entire system can sit idle using just 50 megabytes of memory. 50 megabytes. Yet, it remains fully enterprise scalable, easily handling 20 or more concurrent training jobs on minimal local hardware. That is seriously impressive. So this leaves us with a totally necessary, game-changing question. If we can execute deep reasoning on highly constrained local infrastructure using multi-hypothesis exploration, what happens when we scale this test time paradigm globally? Think about it. If we don't actually need billions of parameters to think deeply, the entire economic landscape of AI is about to change. Thanks for joining me on this explainer. I highly recommend digging into the source logs yourself to see the undeniable proof. See you next time.